module we study about damped free vibrations. So, the outline of this module or lecture is like we study damped free vibration. We will first of all write the governing differential equation, and then we try to find the solution of this damped single degree of freedom system, and then one example problem we will solve in this. So, as you already know, the dynamic equilibrium equation is consists of three forces. The first one is inertia force, the second force is damping force, and the third one is stiffness force or elastic force. And the on the right hand side we have externally applied force, which is a function of time. So, displacement is a function of time, velocity is also a function of time, and acceleration is function of time. This is the vibration of system represented by dynamic equilibrium equation. And in this just to have a recap, we have two kinds of vibrations. One is forced vibration and another one is free vibration. So, free vibration in which force is not applied and vibration is set due to initial conditions, either initial displacement or initial velocity. And in forced vibration, force is applied. So, we are first studying about free vibration. So, we have already discussed about undamped free vibration. So, now in this module we will discuss about damped free vibration. So, wherein damping is present or damping is introduced in a system which reduces the energy in vibrating system. So, this is the general diagram of vibration of single degree of freedom system. As you can see, this blue color slab is representing the mass m, and columns are treated as massless, but they are like resisting elements, that is deformation resistance is coming out of columns, and then energy is removed by viscous damper present in the system, and externally applied force, which is 0. So, is represented by P of t is equal to 0. So, equation of motion as I told you. So, mu double dot plus cu dot plus ku is equal to 0. So, in this damping is a non-zero term. So, it has some value. So, we need to find out the solution of this damped free vibrations. So, first of all we will write this equation of motion, and then for convenience sake we divide all the terms, all three terms by mass. So, what we get is m by m u double dot c by m u dot plus k by m u is equal to 0. So, that gives us like u double dot plus c by m into u dot plus k by m into u is equal to 0. So, critical damping is the damping required to remove vibration energy from the system. So, whatever energy is inputted in the system, a damping which is required to remove all that energy from the system is called as critical damping. We will discuss about it in little more detail a while later. So, that is represented by Cr 2 m omega n. So, this depends on critical damping depends on two parameters. One is natural frequency of the system and mass of the system. Now, this ratio, that means percentage of damping present in the system compared to the critical damping is C by Cr. So, zeta is a term as ratio of critical damping. So, we introduce a new term which is called zeta. So, C by Cr. So, Cr we already know, from this we substitute Cr here. So, we have zeta as C by 2 m omega n. So, critical damping ratio zeta is equal to C by Cr, which is equal to C by 2 m omega n. So, that will give us C by m is equal to 2 zeta omega n. So, this C by m will give us 2 zeta omega n value. So, we substitute this C by m value as 2 zeta omega n. So, u double dot that gives our equation, that converts our equation as u double dot plus 2 zeta omega n u dot plus omega n u is equal to, so omega n square is equal to 0. This omega n square is the term is k by m, and this one is c by m. C by m is this one, and k by m is omega n square. This is square of natural frequency. So now to find the solution of this equation, we are assuming u as in the undamped free vibration case, we are assuming the same term. U is equal to epsilon e to the power of st. E to the power of st, this is a proposed solution. So hence we need two other terms, which are acceleration term and also velocity term. So if we differentiate this u with respect to time, so we get u dot as s into e to the power of st, and then u double dot term we get as s square e to the power of st. So we need to substitute u, u dot and u double dot in the original equation. So when we substitute that and rearrange the terms in the equation, so we get this equation, so which reads as s square plus 2 zeta omega n s plus omega n square multiplied by e to the power of st is equal to 0. So we can observe in this equation there are two things, one is bracket term and another one is e to the power of st term. So for a non-trivial solution, this e to the power of st term cannot be 0, but for trivial solution it can be 0. So that means u is equal to 0, so there is no solution at all. So this, upon working further by making this bracket term as 0, we get two roots from that, s1 and s2, by using usual algebraic principles. So we get zeta multiplied by omega n plus or minus I omega n under root 1 minus zeta square. So this, upon further simplification, so this term omega n under root 1 minus zeta square, we are converting or we are naming that as damped natural frequency. So the earlier one, omega n alone, is a natural frequency, but whereas omega d is termed as damped natural frequency, which is like omega n under root 1 minus zeta square. So this s1 is one root and s2 is the second root. So this natural frequency of damped structure can be calculated like this. So from this equation you can clearly see that when zeta term is 0, damped natural frequency is equal to original natural frequency. So that means what, zeta value is reducing the natural frequency, or in other words it is increasing the natural period of the system, or we can say that because of the presence of damping, period of vibration elongates. Then upon substituting this s1 and s2 in the solution form, we get ut is equal to e to the power of minus zeta omega nt multiplied by a cos omega dt plus b sin omega dt. As you know, these two are the constant terms which we need to get rid of. Now how to get rid of these two constant terms? For that we need to use initial conditions. So we have two initial conditions, that is at time t is equal to 0, we have u0 is u0 and u dot 0 is u dot 0. So initial displacement as well as initial velocity. So these two conditions we need to use. So using initial conditions, these two initial conditions are given here. Now if we use that, what we get is a value as u0. So that means a is a constant which is equal to initial condition for displacement, and if we substitute u dot, so then we get b constant which is equal to u dot 0 plus zeta omega n u0 divided by omega d. Omega d is damped natural frequency, and if we substitute these two things in the equation, that is a proposed equation, so we get this big equation which contains two terms. One is e to the power of zeta omega nt, which is the envelope function, and then u0 cos omega dt plus u dot 0 plus zeta omega and u0 by omega d into sin omega dt. If we plot this solution, we get solution like this. So if it is undamped free vibration, so how it looks like is it will not come down. So vibrations will go without any reduction in the damping energy. But because of the presence of damping in this one, you can see this envelope function. So energy in the vibration is coming down in every cycle. So in every cycle, energy in vibration is coming down. So you can look at this equation, you can clearly see that here the constant term, that B term has zeta value, and cos omega d and sin omega d also contains damping terms in it, and then this envelope function e to the power of minus zeta omega and t is showing this how the vibration energy is reducing. So at any point the amplitude of vibration can be given as the square root of the sum of squares of the coefficients of cos and sin terms, that is amplitude. So this is a square a plus b. So a is a constant term before cos and b is a constant term before sin. So square of a plus the square of b and whole under root will give the amplitude of vibration. So this amplitude of vibration is slowly coming down with this exponential term. Now let's solve one example problem of damped natural frequency, damped free vibration. So in this one we have the roof of one story building has mass 2000 kg. All the columns supporting the roof together offer a lateral stiffness of 30,000 Newton per meter. Assuming percentage of critical damping to be 5%, find undamped and damped natural period of the building. We already know the system parameters, that is mass of the building we know, and then stiffness of the building we know. So M is 2000 kg and stiffness is given as 30,000 Newton per meter. Now how do we find out undamped natural period? So for that we need undamped natural frequency. Formula we know. So omega n is equal to under root k by m. So here we need to observe one thing, k should be in units Newton per meter and mass should be in kg. So 30,000 Newton per meter, and in denominator we substitute 2000. So that gives us 3.87 radians per second as omega. So if we substitute that in the natural period equation, 2 pi by omega, so which is 2 pi by 3.87, so we get 1.62 seconds as a natural period, or so 1 by natural period 1 by t is equal to frequency. So that is equal to 0.62 hertz is a natural frequency, or 1.62 seconds is a natural period. So let me once again tell you, natural period is time taken for one cycle, or one to and fro motion, or one to and fro oscillation is called natural period. Is something like this. So if a building is vibrating, so time taken for this half, coming back, overshooting and coming back. So this is one cycle of vibration. So time taken for one cycle of vibration is natural period, and if body is vibrating, number of oscillations it is making in second, okay, per unit time, that is called frequency. So that is the relationship between natural frequency and natural period. So this is undamped. Now when it comes to damped system, we already know that like damped natural period is 2 pi by damped natural frequency omega d. So now how do we find out omega d? Omega d is already we know the relationship omega n under root 1 minus zeta square. So omega n is already calculated, so 3.87 under root 1 minus, that is 5% damping gives 5 by 100, that is 0.05 square. So that gives us 3.865 radians per second. So if we substitute that omega d in this equation, we get 1.625 seconds. So you can observe this relationship. So damped natural period is always greater than or equal to free like undamped natural period. So this we need to remember, damping elongates natural period. So in summary, what we have discussed and understood in this module, it goes like this. So we have undamped systems and damped systems. So in damped system, like any vibration, damped free vibration, any vibration which is set, or any body which is set to motion, will ultimately come to rest. So the element which is responsible for bringing it to rest is called damping present in the system. So we developed equation of motion for the damped free vibrating system, and then we found the solution. So in solution we could see that there is a continuously a term which is reducing the amplitude of vibration. So that is e to the power of minus zeta omega and t term, and in the bracket we have something similar to free undamped free vibration term. So combination of these two, vibration amplitude is continuously reducing. So and then we discussed about natural period and natural frequency. So undamped natural frequency and damped natural frequency. So damped natural frequency will be higher compared to undamped natural frequency, and damped natural period will be higher compared to undamped natural frequency.